Fast forward.
All right, so Celine, do you want to do the intro? You're
Yeah, sure.
moderate.
So,
All right.
we have, two review talks this morning. So first speaker will be Gordon Richards, telling us about the evolution of AGN discs in the 2020s. And I believe Sylvain Veilleux is the second speaker this morning. And then we'll have a little discussion session, about half an hour, about, those talks and other thoughts that we may have. So I'll, give you a sign, you maybe have 5 minutes, if that's okay, and then we have some time for questions.
I'll be less than that, and then we're gonna retreat.
Okay.
Have it come up.
Yeah.
Or else.
Yeah,
Okay,
I would say, right.
Yeah.
great.
Do you want that bigger or is that fine?
It's good.
Okay.
Yeah.
Okay. So as Celine said, this is going to be a two-part talk with me introducing the topic, followed by I'll note that it's the first time that either of us have given this talk. You all will be the judge of whether we ever do it again. I hope this is a talk that you weren't expecting, the organizers included. Okay, so with the advent of the 2030s, some of us would like to skip ahead a few years, 1,402 days to be exact. I thought I would start by reviewing the state of accretion disk theory in the 2020s from the point of view of an observer. That is, I'm not an expert in accretion disk theory. I'm just an interested user. And full disclosure, almost none of this is my own work, and most of the slides aren't even my own. Okay, so if you've ever attended a talk on quasars, you've probably seen this figure from Uri and Padovani in 1995. As much as I respect their work, I had generally have stopped showing it because nobody thinks that quasars look like this. Okay, well, I mean, maybe they do, but not really when it comes down to it, right? And so let's take a minute and we're going to review the basic parts here, right? So we have roughly 40% of the SED comes from each of the IR and the optical UV, and 20% from the X-ray, with a small fraction having a significant amount of radio. The host galaxy is much fainter, something like 1,000 times in the UV. And then we have both the broad and narrow lines that occupy magic. Okay. And so I tend to think of things, instead of a single SED, I tend to think of things in the way that Matthew Temple has nicely illustrated here, using Chris Stone's QSO SED model, where the thing that matters the most is the fact that the X-ray doesn't scale linearly with the UV, right? So that's the well-known LUV alpha X relationship. So if you double the UV luminosity, you don't double the X-ray luminosity, and that significantly affects how things work. Okay, so I really liked these cartoons from Giustinian Proga 2019, which showed a schematic of the physics. On the left, we have the cold optically thick accretion disk in green, and the hot optically thin X-ray corona in red. The SED contributions of each are shown on the right with the same color coding. Specifically, so each row, so going down, M dot is increasing, and going across, M is increasing. So on the left, we have physical schematic, and for two of the M dots, we have two black hole masses. And then what you're seeing is the SED that results from each of those panels on the right. Okay, so higher mass, when we go from left to right, gives a cooler disk. So you're shifting basically the green component of the SED over to the left to longer wavelengths. And higher accretion rate means changes in both the shape of the X-ray SED and the relative amount of X-ray to the optical UV. Okay. Until the mid-2020s, the standard accretion disk model was a so-called alpha disk prescription from Sakura Sanaya of 1973, which indeed underlies the cartoon that I just showed. It was actually developed to explain binary systems, but did a pretty good job of scaling to larger black hole masses, explain AGNs and quasars. Indeed, I recall reading it as a graduate student and thinking, you know, if I didn't know what the publication date was, it could have been easily the late 90s and not 1973. Okay. As well as that model worked for AGNs, it had been long known to break down in certain situations. Specifically at low accretion, Narayan and Yee and others found that radiation is inefficient and the heat gets trapped and is transported inwards, resulting in a puffed up inner disk. Somewhat ironically, something similar happens at high accretion, where again, the radiative inefficiency causes the disk to deviate from the classical model. In addition to the disk itself, there are changes in the scale height of the corona, as illustrated here by this cartoon from Veilleux et al. 2004. So we can see the X-ray corona, you know, illuminating the disk versus not illuminating the disk. Okay, in some ways, these were small tweaks to Shakura-Sinai of 1973 and not attempts to overturn a paradigm. However, there were even more holes in the model. While not intended as such, I might argue that the first draft of the obituary for SS73 as applied to AGNs appeared on the 6th of July, 2020 in the form of Davis and Tchaikovsky. So these quotes from that paper, I think, presage what was to come. So first, the standard model does not consider the impact of magnetic pressure. Okay, think about that. The second thing is, a key is why there is seeming discrepancy in how well the standard disk models reproduce the properties of AGNs and black hole XRBs. So this is specifically talking about why Shakura-Sinai of 73 works very well for binaries, but doesn't necessarily work as well for AGNs, and asking, you know, why exactly might that have been the case? So they note that a consideration is the impact of the different environments and feeding of the two systems. AGNs are thought to be fed predominantly from gas in the large-scale interstellar medium of their host galaxies, whereas the X-ray binaries are fed by Roche lobe overflow from a companion star. In addition, they have different ways of shedding angular momentum. Okay, so back to magnetic fields. They ask, what role do magnetic fields play in AGNs? Does magnetic pressure support change the structure of the disks? Is there a reason to believe that magnetic field geometries differ between AGNs and X-ray binaries? And then they say, one might expect the disk to lose information about its large-scale feeding. This argument may not hold if the large-scale geometry of the magnetic fields is influenced by the condition of the outer flow. Okay. So with that, so while the date of SS73's demise with regard to AGNs and it is still debated today, there was a host of work by many researchers in the field on non-SS73 models and accretion disk modeling, you know, before that this time. But I've adopted a date of the 28th of June, 2024 as the date of the final demise of this model for AGNs, namely with the advent of this paper from Hopkins. So it took some time for beyond 2024 for astronomers to realize this for a number of reasons. First, because this wasn't really one paper. It was at least 5 papers, almost 200 pages of very dense text equations and figures. And second is because we all have this predominance of the idea that invoking magnetic fields is sort of the last bastion of the desperate. You can do, you know, anything you want as long as you invoke magnetic fields. Okay, so the rest of this talk is my retelling of the story. And that story starts with recent simulations have demonstrated the formation of flux frozen and hypermagnetized disks as a natural consequence of fueling gas to supermassive black holes in galactic nuclei. Okay. All right, so here we have the black hole, ironically not black, but gray. And out past the innermost stable orbit, or ISCO, is the gas of the accretion disk. In the standard SS73 model, the magnetic fields are not important components of the accretion disk. And what fields there are colloidal. So what that means is they don't do anything to prevent the spinning gas from collapsing into a thin disk. And a consequence is that, as I've already highlighted, there are many problems with this disk model as applied to AGNs. Okay, so these disks are gravitationally unstable, they're too hot and too blue, they don't explain the observed soft X-ray excess, and the disks are physically too compact. All right, so moreover, the things that make up the majority of the AGN SEP can't actually exist in the disk itself. The physical conditions simply aren't consistent, right? So you want an X-ray corona, fine, but you can't put it in the disk. You want a soft X-ray excess, fine, but you can't put it in the disk. You want a broadline region, fine, but you can't put it in the disk. You want a torus, fine, but you can't put it in the disk. So you have to have these things sort of magically outside of the disk and floating there. So we've adopted this cartoon model that if you could magically create, right, would nominally give us the SED that we wanted or needed, right? But there's no concrete physics behind this, just a need to explain basically what it is that we saw. Okay, so in the course of simulating fairly realistic galaxies, I'm sure you've seen simulations where you see one fake galaxy and a real galaxy and you can't tell the difference between them. And then basically following the physics to the scales of the accretion disk, Hopkins and collaborators showed that it was possible to start with very weak, very disorganized magnetic fields on the order of 10 to the minus 5 Gauss. So the tangled blue lines in the upper right-hand corner, and end up with rather strong and organized toroidal rather than poloidal fields of order 1 Gauss at scales of in the accretion disk, right? So in the left here, right? And you can see how the magnetic fields are scaling with the size, starting with really very, very small magnetic fields and just following what happens as it gets down to the scale of the accretion disk, not invoking a magnetic field sort of out of nowhere. Okay, so the pressure from those toroidal fields exceeds the thermal pressure. And so they resist gravitational collapse, generating a thick disk. So how thick? This can be seen here, really quite thick with a scale height that's something like 10 to 100 times larger than the SS73 disk in the outer parts of the disk. So here, the black, solid black line, I guess it's not. Where's this pointer?
Pointer, yeah.
Right, so this is showing the Hopkins model of the accretion disk. And then we're seeing two versions of the classic thin disk model for m dot of 1 and m dot of 0.1, right? And I want you to realize like that this is the scale height of that of those disks, right? So yes, for m dot of 1, your very inner disk, your slim disk is puffed up, but for most of the scale here, you're getting a radically different size of the accretion disk. So Hopkins highlights a number of differences from an observer's perspective. My perspective, these were generally quite welcome, right? So we have magnetic dominated disk, very thick and flared, scale height of order 1 with radius, right? You need much lower masses in these disks. They're gravitationally and thermally stable. They're more extended. They have cooler thermal region. They also have scattering. And really a significant amount of the flux is, there's some self-illumination, there's scattering, there's comptonization, and so on. Okay, so that simulation started from a black hole mass of 10 to the 7, but it brackets the knee of the quasar luminosity function for a range of efficiencies at redshift 4.5, and has accretion rates of like 20 to 30 solar masses per year. So they might not have been simulating hundreds or even dozens of objects, but even this one simulation already is pretty interesting. Note in particular the coherence of the magnetic fields and the inversions. So this is 3 different scales. So this is the poloidal magnetic field and the vertical magnetic field and the radial magnetic field, or I might have those reversed. And so you can see the color coded by the different polarity. So blue and red showing positive and negative polarity. And the implied magnetic flux inversions were pretty intriguing for things like changing state AGNs in the mid-2020s. So, and note that those magnetic field lines are still below the MAD limit. Okay, so the broad cartoon of that model looked like this. So Hopkins noted, we show there are several characteristic zones, a dusty torus-like region, a multi-phase neutral, and then multi-phase ionized broad line emitting region interior to the sublimation radius, before finally transitioning to a thermal accretion disk with a warm Comptonizing layer. We're noted to be part of the accretion flow if the disks are hypermagnetized in the hypermagnetized limit. This is a lot to take in at once, and so it gets a second slide. So the green zone here is the broadline region. The brown being the torus, both as part of the accretion disk, as is the soft X-ray excess emitter, quite unlike the SS73 model. Zone 6 here produces the big blue bump, most of the optical UV continuum. And they note that the warm, about 1 keV Comptonizing structure covering the thermal continuum source needed to explain the soft X-ray excess was noted to be seemed to be inevitable in these flux frozen disks. Zone 7 was identified as the more diffuse extended hard X-ray corona, and that X-ray hardness was noted to decrease with the Eddington ratio, but otherwise was beyond the scope of this work. In zone 8, they commented that the scattering surface will both influence the inferred microlensing and reverberation mapping time delays. So of particular interest to me was the scaling with the effective temperature in zone 6. For over 20 years, theorists have been asking me why SDSS quasars are backwards. This could explain why. Okay. So instead of going as L over M to the small power, the flux frozen disk go as M over L to an even smaller power. So they're basically even less sensitive to black hole. Okay, so Sylvain will take you through the changes in the outflows that occur with the changing accretion rates. But I do want to take a quick look at how the X-ray through optical SED changed with the accretion rate. Okay, so for moderate accretion rates, we have our X-ray corona, we have our soft X-ray excess, and we have our big blue bump. So X-ray corona, soft X-ray excess, big blue bump, still the broadline region here. And then if we go to super Eddington accretion rates, we have our lamppost X-ray corona. We have an extended soft X-ray excess region on the big blue bump here. And then, so this is particularly interesting to me. At low enough accretion rate, zone 6, that's where the big blue bump was, that shrinks below the ISCO, and we lose the soft X-ray excess producing region, but have a very extended hard X-ray producing region. So even lower, you get an ADAF like hot flow with minimal ionization broadline region. And indeed, at low enough accretion rate, we see a significant change in the structure, very similar to what Hagen et al. 2024 argue must be happening based on empirical data. So in this upper right-hand figure here, the pink is the classical accretion disk. The purple is the corona, and the green produces the soft X-ray excess, and this soft X-ray excess region is squeezed out by the other two components at at low accretion rate, right? And so I note the loss of the BLR in the Hopkins model, providing a potential mechanism for changing state objects. Okay. Since this is a meeting nominally about surveys, in that context, we can ask a number of questions, right? So could this model produce the radio through X-ray SEDs that we observe? Okay. Can it produce the variability that we observe? Can it explain reverberation mapping and disk size results? Can it explain changing state sources? Can it resolve discrepancies between AGNs and X-ray binaries? And can it do all of that as a function of mass and accretion rate? So, yeah, I don't know. There's much work to be done to answer these, but from my perspective, I would argue that this is where we should be starting the discussion rather than from the so-called standard model. Thanks, and I'll turn it over to Sylvain. I mean, you can ask the question, but we're going to take them afterwards. So
Yeah, and I mean, one question here, like if you have like a, one or two questions, I think.
Gordon, this thin BLR layer, that's sufficient to explain what lines as we know them?
So, I mean, one of the things they emphasize is that it does give you about the right percentages. I mean, so your covering fraction has to be right. And, one of the arguments is it does give you about the right covering fraction in the sense that, like, I don't know, 10 to 20% of your rays are intercepted by that region. And so your line emitting flux to continuum is about right.
Is it dynamically, stable, or being part of the disk, is it inflowing?
I mean, Sylvain's going to talk about outflows now. I mean, that's something we can talk about. Anything else pressing before?
Yeah, any other question I see? How does this kind of disagree with the post-COVID 20 model that say that it's a magnetic accretion flux that can launch jets maybe and in relatively efficient regimes?
I'm going to talk a little bit about that.
Not a match.
Did you have a question?
Can I ask now, or I can ask later?
Yeah, that's.
Yeah.
It's more like a detailed question, but in Hopkins simulations, is ideal MHD, or they include some non-ideal?
So I do not do this work, right? So
I can even look at the paper. Yeah. Okay.
yeah.
Okay, so let me pick it up from there. Part two. So I'm going to emphasize but I cannot avoid talking about accretion that's solved from. So going back to that picture, this is a nice idealized picture, beautifully, not flaring, by the way, as you notice. But the reality in these models, at least, looks more like that, different scales. So going from, I work in parsecs. I guess all the models are in RGs or astronomical units, but so from 0.1 parsec scale to 10 to the minus 5, all the way to basically the event horizon scale. So this is face on, this is edge on, this is also edge on, but azimuthally average. I don't know if you can see the detail, but the point is that, okay, it's thick, but there's a lot of structure above and below the disk. There's flaring. So anything, if there's radiation coming out from the middle of this structure, it's going to hit material that is above the disk and below the disk. It's going to get absorbed. It's going to get scattered, ionized again. We'll have, as Gordon mentioned, reprocessing. And that explains a lot of the observation themes. So since one of the topic that has not been covered yet is the wind, I want to talk a little bit about what radiation can do to the material in the structure before I actually show you the results from their simulations. I just want to mention, obviously, radiative feedback, that all this radiation coming from the center will illuminate, ionize, heat the disk, the torus, and then, of course, much beyond, send the galaxy, the gem, proximity effects, etc. It's also going to push on the material. Now, of course, that's not the only force that will take that. And so I go back to my, one of the formula that I use in my own review. Now, of course, I'm going to ignore all of these. It's thermal pressure, cosmic ray. They, in Hopkins and collaborators, they claim that the cosmic ray pressure is actually not significant. The jet, they talk about it a bit later, so I'll come back to that. But there's also a component about magnetic fields. This, yes, presumably would be included here. But the point is the radiation pressure here. This is a formula that was for global effect. Of course, in their models, they look at the local effects, so the flux, not the luminosity, against gravity. I just want to emphasize this radiation pressure term. That's actually a formula that comes from Hopkins 2014, actually. And it's a nice formula that sort of encompasses everything about single scattering, but also multiple scattering if there's really high optical depth. So for the simple, single scattering, it's just basically this comes down to UV optical depth, what we know and love. But in the case where it's highly optically thick due to dust, so we're beyond the sublimation radius, and that term, this tau effective, can become significant. But it only becomes significant, this tau is of order 1 only when it's Compton thick. So in most cases, 0. You just have that single scattering term that we usually use. But if the optical depth, if dust becomes important, so beyond the dust sublimation radius, I mentioned that because when it comes time to talk about the torus, it becomes important. So where dust survive a radius beyond about 0.4 parsecs, given the luminosity and the temperature, the silicate construction. In that case, if dust survives, the main point is that if dust is present, then it completely dominates the absorption of the radiation. That radiation pressure completely dominated by its dust, the radiation pressure on the dust, much larger than it scattering or driving. Okay, so that's just setting up this, coming back to nice cartoon that Gordon showed. So the arrows here are the winds that are predicted model. So basically nothing on smaller scale, big blue bump. Maybe the scatter region has some outflow. The broadline region, this picture, this is m dot of 100, mind you. This is really blowing. This is super Eddington, super Eddington accretion. The broadline region are expected to be pushed away. Then the torus in brown also, because then the dust dominates. And so notice the arrow is actually larger because the radiation pressure is on dust now, in a way boosted due to the dust. And the same thing for the outer regions, the narrow line region would be here. It also, where dust is present, the outflow can be quite large. So this is for m dot 100. M dot 1, of course, arrows, the velocities are smaller. And then m dot 0.01, basically only perhaps the dusty torus is being pushed away in the narrow line region, and basically nothing else. The broad line region affected by wind. However, there are limitations to the models. They don't actually model the line driving that would be important for the broad line region. That's a big caveat here. So here's the predicted inflow and outflow rates. So the solid lines are the inflow rate. The dashed lines are the outflow rates. So the green, sorry for color blindness here. I didn't make the plots. The green are the m dot of 20, so super Eddington. The purple, I guess, mauve are 0.3 m dot. And this one is 0.02. So of course it scales as you increase with m dot. The values are pretty substantial. A lot of inflow, of order 10, I guess, on this scale. Solar masses per year. The outflow are less than the inflow in essentially all cases. It drops dramatically at small radii, which could be a limitation of the models. The point is that these numbers are quite substantial for both, of course, the inflow, but also for the outflow. So a bit more detail. So focusing on this is radiation field going for, again, for m dot 20.3.02, more, I guess, collimated radiation field in the higher m dot case. Here's the velocity field. Green means it's outflowing away from the center. Purple means it's outflowing away from the center, but in the negative direction, the Z velocities. So this is a nice case of outflow, 20. not the case for 0.3 or 0.02. It's the opposite direction. Gas isn't flowing. Part of the accretion picture. A lot of accretion takes place in the disk, but in this case, there's also accretion even in vertical direction. So only in that case is there an outflow here, massive outflow. This is zooming in on the 20 case. This is basically zooming in the structure here on the inner 500 redshift radius. Well, everything is green, it's beautiful, it's outflowing very fast. The velocities are, this is 10 to the 5 kilometers per second, so it's becoming almost relativistic, at least slightly subrelativistic. So around this region here, we're talking about very high velocity. That may actually be similar to what we observe warm ionized in the warm absorber, and the more extreme case is the ultra fast outflows. So it was all nice and good. It might be able to explain the UFOs even in this picture, in this simple picture, where most of the outflow is radiation driven in this picture. Now the problem is you go out on larger scale. Again, this is all inflow, so let's not worry about that. But this is the outflow, and notice the outflow basically stops on scales of 0.01 parsec or so. So we're dealing with a failed outflow. Maybe you have a UFO velocity here in the center. It doesn't go very far. It just stops there. It fails. So there's in that paper, this is the Hopkins 2025 model. It fails even in the M dot case of 20. Just disappointing. I was disappointed. I like outflows, and I know they go further. But there's numerical limitations to the simulations. It's not easy to run these simulations. There's no radiation line driving, as I mentioned, that would affect the broad line mix. The other thing that's really important is in this particular paper is the running time. I mean, again, it takes a lot of CPU to run these simulations. And the running time affects anything that is beyond basically that scale. The dynamics has not had time to react to what's happening in the center. And so the driving of these out, you can't basically trust anything much beyond this sort of radius, beyond 0.5 to 5 times 74 RGs, which is that scale here. And there's no GR in this particular model. But of course, Phil, being what he is, collaborated with his friend who do GR. And so within a month, they had another paper or so on astro-pH, the CATS paper, where they do include GR. So this is building up on the same picture. This is flux frozen disk on large scale, which is this a new cartoon here, where you have the toroidal magnetic flux that dominates on large scale. But on smaller scale, they find that the loops are advected and they break open. But within about 200 RGs, it starts breaking open. And that's what's shown in that cartoon, these lines that comes out like this. And of course, that's a good geometry to drive winds, but magnetically driven winds now this time, not radiation driven winds. The radiation driven wind would be on larger scale, but the driven wind would be this sort of scale, 200 or so RGs. So, perhaps these models are more reliable in corona. That can be debated, but they do have jets. When the spin of the black holes is large, they have two cases. One case with zero non-spinning, they have no jets, but in a case where it's fastly spinning, they do produce a jet. The main idea, though, is the toroidal magnetic field dominates on a large scale. The vertical magnetic field builds up in the center, again, within about 200 RGs. And then they produce a jet through the Blanford-Gagnac rhythm zigzag that spin down, actually significantly spin down the black hole as expected. In fact, it does it within 5 to 10 million years, which actually may be a problem. It's very fast. Okay, so let me just show you a few pictures. It's just the cartoon. This is a few of the picture. Again, on different scale, 0.1 parsecs all the way to 20 RGs now. Right? Again, this is the event horizon. I mean, visually, the structure looks similar to what it was before, but there are many fields. The total many fields dominates on large scale. This is all the way to times 10 to 4 RGs. It dominates on large scale compared with the vertical, but then it crosses over. So within about 200 RGs, the vertical many fields dominates, and that's when it's very helpful for these outflows on that very small scale. And it doesn't matter what is the spin of the black hole, non-spinning or fastly spinning, basically the results is the same, which is quite interesting. So this geometry, this change in geometry doesn't care about the actual spin of the black hole. You have to include the GR ingredients for this to happen. Another, I think this may be the last, this particular paper. What is shown here is the energy. This is radiation, this is mechanical, it's basically all the energy in the flow. And in this fast spinning black hole case, the energy is very well collimated. Let's see here on scales of, again, 10 to the 4 RGs or so. In the case where it's not spinning, it's much less collimated. Also, the energy is much less in general. So here are the numbers that they find for fast spinning black holes. They get incredibly efficient outflows that can be debated. Those are the numbers. The energy of in the outflow is 60% of the accreted rest mass energy. The energy in the radiation is also very large, 100% of the accreted rest mass energy. This is in the fast spinning black hole. In the non-spinning black hole, they're still getting pretty large number in the outflow, 10%, which would be enough if it goes far enough to produce feedback. And so even that number is quite large. These lines here that are shown, so the photosphere is where the last photon comes out. And so if we were to observe this black hole, they say that basically we would see only the surface here, this last surface. This is tau of 1. And so we would observe this black hole, that's the surface we would see. We would not be able to see in the middle. Anything within this line would not be seen. So this scale is quite large, talking about 1300 AUs. And so that also explained the fact that the disk scales, the disk size are measured from or derived from microlensing, etc., are large in this model as well. So they're able to explain those sizes observed. Because basically there's a lot of scattering and it makes the photosphere quite large. Okay, so can it, I'm interested in observation. Can it explain things quantitatively? It seems like they have no problem explaining ultra-fast outflows or warm absorber. They certainly can get the velocities. Question is, do they get the mass? It's not, there's no, I would say, quantitative prediction in their models, but it's certainly tentatively that they will be able to explain them. It can be done either from radiation. This was in the Hopkins 2025 paper. In the Katz paper, then the magnetic field, winds would be able to explain these. We know and love, and Gordon spent quite a bit of his career showing that the kinematics, the dynamics of the broadline region, also in some cases, is outflowing. Right, and that's especially true for the weak-line system, X-ray Fein system, high Eddington luminosity, where basically the blue shift increase with Eddington luminosity, and as the with forward decreases. This is wonderful statistic. I go back to my favorite object. I cannot, I had intended to talk about other topics with you
Yeah.
I cannot avoid plugging that Hopkins 231, which is also another objects where the broadline reads are highly blue shifted. It's an X-ray faint system. It's a weak line system. Obviously, a wind dominated. It's a very high Eddington ratio. Everything is blue shifted, basically. H alpha looks pretty normal. Look in the optical, looks pretty normal objects. If you look in the UV, the Lyman alpha is highly blue shifted. Carbon 2, carbon 3, carbon 4, all the broad lines are blue shifted. And then the observer, the absorption also, 5,000 a second. And so, I know there's probably some discussion about LRDs in the first week, and there'll be discussion in the last week, which I'll miss. Well, but has a SED that looks a bit LRD-ish in the sense that has a break. It's like a roller coaster, just like LRDs. It drops like a rock around the Balmer line, Balmer jump or limit, and then it's still detectable in UV. So we noticed that in 2013 and 2016, we had to explain this weird SED and all the broadline region blue shifted. So we had our little cartoon, which maybe coincidentally looks a bit similar to the Hopkins cartoon also, where the broadline regions are outflowing. And we're still able to observe the UV in the center. Okay, so last few minutes, I don't know how many minutes I have.
5.
Okay. I promised I would talk about torus, the dusty torus. Well, unfortunately, these models, the Hopkins model, don't make. So this is the whole picture of their models, going from the intergalactic scale, circumgalactic scale, galactic scale, etc., galactic nucleus, the sort of kiloparsec scale, black hole radius of influence, and then finally the torus, which is parsecs or subparsec scale. So the torus is not beautiful torus, of course. A lot of structure, it's symmetric in this particular example. It looks beautiful, except there's no prediction of the SED in these models, unfortunately. There's no predictions of the wind that comes out of the torus. At least no quantitative. There's a few numbers on larger scale that one could use, but in this particular 2025 paper that talks about the center, the predictions, because it just basically doesn't run. The solution is long enough. So we have to rely on these possible simpler models. This is just one of many examples of having a torus like this, large scale and small scale. Of course, you eliminate from the center, and you expect a temperature gradient in torus. And this is the prediction of the flux. This is in 0.5 micron. So in the visible, you have scattered light. So that's why it looks a bit more fuzzier than this is at 4.6 micron, really nucleated, and all the way to 12 micron, a bit more diffuse, because that's the cooler dust is more extended. So that's the prediction. So what, the observation, that's I just grabbed a couple of slides of latest results. So this one is from gravity. That's a K-band. That's a combination of gravity and Keck, actually. So this line is basically the subliminal, the sublimation radius. And the size in the K-band is a bit larger than that, especially at lower luminosity. So this is the same relation divided by this line. So it shows that there's an excess above the line at maybe in the less luminous system. So the torus is a bit more extended than the sublimation radius, especially in the lower luminosity system. While it's very compact, basically consistent with the sublimation radius. So very, very compact at higher luminosity is what is found at K-band. So this is really the hot dust.
One question, there are different objects, right? The
Different
kind of
objects.
Gravity, there's no overlap.
That's a good question.
Would be, I think.
I think there might be a few overlap.
Especially amber and gravity.
Some of the points overlap, right?
Some of the points
The low thermal luminosity, the
like
second.
this, right? And frankly, I don't remember reverberation also that here, the blue is become reverberation map. Red. But in terms of these two, maybe this one is an overlap. And it seems consistent within the error bar. Of course, now there's more results at longer wavelength with VLTI Metis, VLTI Midi, beautiful result, which I can't go into in great detail. I'll just grab one of the latest paper that combines basically the K band, the as I said here, the L, M, N bands. And the result seems like the size are pretty compact. It doesn't vary very much with wavelength. And so most of the emission seems to be within 3 to 10 sublimation radius, even for the longer wavelength. This is pretty flat, essentially consistent with flat. In this particular paper, they also noticed these are for just two objects, but pretty highly luminous objects. They don't notice any elongation. It's pretty symmetric. There's no particular polar elongation, which they say they detected at lower luminosity, not in the higher luminosity system. So they think that maybe that's the possible cartoon to explain that. Low luminosity, low Eddington luminosity, you have a more polar orientation where the dusty wind that comes out of the dusty torus looks a bit like this. And at higher luminosity, it's wider open. I'm just reporting. So, but clearly, you know, we're at the stage where we're starting to constrain that. And it would be nice to compare with the simulations that were discussed earlier. Okay, others. And I don't think we're at that stage yet, but I think we're really, really close. You know, the observations are tentatively showing something. I think the model's just a matter of putting some effort in showing what are the predictions. Okay, so summary. Okay, provocative again. SS73 maybe dead? Question mark. I think the nice thing about this model is that it comes out naturally. You just accrete material, doesn't have to be magnetized, but the magnetic field builds up from accretion. You build up this very strong toroidal magnetic fields. Solve many problems, as Gordon mentioned. And I think they qualitatively explain many of the observed wind and torus properties, but quantitatively, it would be good to compare a bit more quantitatively with observation. I guess I have my own questions. No, they don't have line driving here. The VLR kinematics cannot be predicted. And I wonder if it affects the accretion to structure. I think the bump, it might be, has to be self-consistent, and it's not in that sense with the VLR kinematics. The wind launching in the torus, the larger scale, which I'm interested in, I think it would be, because of short running time simulations, most of the numbers are not in the paper. It might impact the torus structure and perhaps beyond. So, because that's when dust dominates, then it will affect an NLR and Black host and beyond. I would have talked about the CGM at this conference, but
Next week.
well, I won't be here, unfortunately. You neither. So jet or no jet, I think, that paper by Kutz is really tantalizing. I mean, it's a very nice effort. It would be nice to know if it's a fluke, to do a little bit of magic and the jet appears, which, it's not the first paper. Tchaikovsky has a wonderful history of producing jets in his models, and it's a question of statistics. When do you get a jet and how does that compare with the statistics that we know? Observation, that's an open question. And then variability, I think that's our interest in variability and changing state AGN and that. Yes. They do talk about variability, they don't go much beyond that. They live in the theoretical world, and they don't explain the consequences in terms of observation. You would be able to. Okay, I'll stop here.
Any questions? Yes, Vinny?
Sorry, I was mentioned by one of you, but do they provide any analytical approximations to some of the key components? Because that's one useful thing with the now dead or long dead Kurasuniaev
Yeah.
toy model is that you can play with it.
Yeah, they have a bill as a one author paper, the 2024 paper. I think it might still be released. It's been published yet, but on SRPH. And it's all analytical formula.
So it's just approximations to what they see.
Approximation to the complicated functions.
Does it agree with some physical intuition?
Uh,
Or is it, sorry to be provocative also from the side of the room? I ran a huge simulation, I feed the results, this is what I get.
Yeah, no, I mean, I think when he goes through the physical explanation, again, it's a 30-page paper. It's not done briefly, but he goes through that.
I mean, I think if I had a criticism, I would say, devours the literature. So he knows the answer he's trying to get. Maybe it's a little convenient. It's the answer that you want.
We put it in practical terms and perspective. Last week, there was some discussion about momentum conserving outflows, energy conserving outflows. The fitting formula he gets are in agreement with one of these scenarios on any scale, or favor one of these scenarios at specific scales of interest.
I think he goes into choosing between one versus the other. I mean, one thing is that he talks a bit about the X-ray, the corona, where the alpha physics of the radiation pressure is easier to understand and with it analytically. When it comes to the broadline region, again, it's like the models, there's a weakness here because the models are incomplete and therefore, the explanations are incomplete. But I mean, basically, what I'm saying is that, he's able to explain basically everything that we know about AGN, both in terms of the structure, the sizes, etc., but also in terms of feedback. You may not be fully satisfied with the answers because they're not fully developed, but I mean, I think it's a pretty strong paper in that respect. It's a good starting point, certainly.
Yes. Thank you.
I think Gordon mentioned it earlier, the disk sizes from reverberation, from continual reverberation mapping and micro lensing, they were always quite far off Kurasuniaev. Does this match better?
Yeah. Well, that factor 5.
Got the factor, sort of.
Yeah. I mean, that multiple scattering, that photosphere, well, this is not the original. It's including the GR. I don't think there's a figure showing the photosphere in Bill's paper that I remember. But the point is that these lines, the photosphere, I guess you don't see my cursor. Quite large. They never come close to the picture, which would be very small. And so that factor explains that also my size of those discs is larger than what you would expect from 73.
So before we move to the discussion, I see 2 more hands. So Paula, do you want to go first?
Well, is there any discussion about the timescales from this model? Or changing the ends is a problem with additional models playing timescales observed. Any discussion about that?
Yes, sort of, in the sense of they do sort of follow, for example, the magnetic flux inversions with time. Right, and so you can see sort of how long it takes for you to accrete a particular band of magnetic flux, and then have it, you know, the sign flip on you, right? Yeah. But I mean, maybe not quite what you want, right? But
Yeah, so I mean, that last paper has this semi-complicated plot that talks about accretion rates. This is the accretion rate as a function of time on for the non-spin and spinning, the mass accretion rate. So you know there's time scale here, and then they follow other quantities. But the point is they do have the accretion rate, and it's probably more reliable as the GR one than the other. And so there's definitely information. There's really interesting information actually. If you start looking at all these figures, you have weird phenomena going on. Like you mentioned, like Gordon mentioned, the reversal, for instance, that's a case where the flux is in one vertical direction, that positive, and then if it creates flux that is in the opposite direction, so it flips, and then so momentarily it kills the jet. That's what happens here. That there's no more jet. And then it starts reaccreting, and then it jet. And so you have these cases. It's not quite changing state AGN. We don't go into that, but they seem like they have the information to go from that to making actual observationally testable predictions.
Okay, so one last question and we move to the discussion.
First of all, thank you both of you for giving this beautiful review talk. I learned a lot. Actually, I have two questions, but okay. The first question is near the end of the second talk. You mentioned that Hopkins model can explain something that Chakra-Sniper model cannot, and I'm wondering if there are some things that both models can explain. And the second one is in this Hopkins model, I'm wondering whether whether all the things that we see are actually transient phase, or it's actually more like a quasi steady state. It's a long-term phase or it's a short-term.
Well, according to them, I can answer maybe the second question is that's pretty long-term.
Okay.
Except for these fluctuation of n dot varying, it will stay like that. As long as there's accretion going on, larger scale, you spin it around and you get the total fields, and that's the state it's in. As long as you keep it feeding it, as long as there's no gas accreting. Of course, if you cut off the supply, then eventually it will die out. But you keep feeding it in the same fashion. Produce, I think, my understanding of these models, that it's going to stay in that total geometry, and everything that's discussed there would apply.
And I mean, as for the first question, I mean, yeah, we spent the last 50 years studying circuitous night, of course, right? It explains some things pretty well, and so both.
So, for example, what kind of features that both models can explain reliably, I would say?
Well, the big blue bump is explained in its own way in both models. Just that the exact size and how much mass is involved, it's quite different. Some numbers are more comfortable than others. And it says 73, and some of the numbers like that, the disk mass were quite large, and the fact that it was unstable. I mean, it was predicted, it still was predicted. Star formation at an incredible rate. You might like it, but I don't really like it in that respect. And in this model, star formation is prevented. It's stable.
Good. So I propose we'll put some chairs here for the panel members to come and sit down with us. Perhaps. Yeah, okay. Yeah, let's take this one. Thank you.
Who are
One thing you are.
we are?
I don't know, how many of you, 3 of us, or,
I don't know.
okay, nobody else?
Good. I think 2 and 2, right? 4 altogether.
So, we have. You want to find a few words just introducing yourself? We have
Yeah.
Gordon and Sylvain, you know,
Yeah,
I want
sure.
to give you a chance to introduce yourself. Is that okay?
Yeah, sure,
Yeah?
sure.
I'm letting her.
Guys, please.
Oh, okay.
Please. Do this.
Yeah, so hi, I'm Marzena Śniegowska. I'm working at Tel Aviv University with group of Bani Trachtenbrot. I'm working on changing look AGN from observations and from theory. And in theory, I'm using Shakura Sunyaev. So I will try to kind of defend my work. Yeah. Okay, yeah, so I sent a slide with some discussion questions. So
What do you mean this one?
I sent it to Ben
Okay, great.
Yes, okay.
email.
When did you send it?
Half an hour ago to Colorado. I can resend it if you.
You told me.
We can stay with the questions which were in the previous talk. It's
Yeah, you told me you sent it and then I forgot about it. Wait a second.
because also we can just go on
Yeah,
the
I'm
discussion
sorry
as it
about
was. It was also quite interesting.
So, I mean, while you try to find that, I guess, maybe some context here that is maybe of interest is that. So Phil first sent me the single author paper about a year ago. It normally takes like 2 weeks to get on my reading list. I dropped everything, started reading it, and then I was like, oh shoot, I've got to read the other 3 papers that lead up to this. And then I devoured them. Right. From an observer's point of view, I mean, I'm skipping over all the equations, just going, yes, I love this, I love this, I love this, I love this, right? And then, a month ago, right, I suggested Savannah, I was like, hey, do you want to approach this talk from this point of view? And you can see that, I mean, you've got other things to do, right? I mean, he also, must have dropped everything and basically, read 5 papers, right, which are pretty dense, right?
They're on my radar, so
Yeah.
I'll read them at some point.
And I think
Give me the incentive to actually read them.
exactly. So if we've done nothing else, right, just provide some incentive to at least skim through what I think is a pretty interesting sequence of papers, right? So
That's the point is well.
Yeah.
Yeah, sometimes.
Could I ask about the X-ray corona and the warm corona, the hot corona and the warm corona in that model? Does that come naturally out of the simulations? And what is the mechanism that is heating the gravitational flow?
So, I mean, yes, right. Again, to what extent like Phil knows the answer he's trying to get, and then therefore, says, oh, I'm going to identify this region as the soft X-ray excess. But I mean, he does have the corona, and then you get this sort of, thin layer on top of the big blue bump in their model, right? That is basically the source of the soft X-ray excess, which, and Chris Doan has done a lot of nice work, and others as well, sort of showing that you need this third component, right? You can't just have the cool accretion disk and the hot X-ray corona. You need something else, but that something else is a function of L. Eddington, whether it is completely dominating the SED or it just sort of doesn't, exist at all, right? And so,
In the last one, the cat's paper, they have a jet. You look at the figure carefully, like that photosphere picture that I showed. There is actually an enhancement of emission. Like if you love the lamppost model for the corona, the hard corona, they have hot spots there, which is I'm not sure they go into discussing that. But I missed it in the 30 page. But it's intriguing that it's there. They do talk about the lamppost model. So they, doing a GR, they seem to be able to reproduce it. But they also say that a nod in terms of the strength of that lamppost versus the more distributed corona that they also have in the model. No, it's again, it's tantalizing. They don't model the temperature, the fluid temperature though. There's limitation in the corona. The two fluids have to have the same temperature, electrons and one. And so there could be some limitations in the by hard X-ray. That's one caveat.
Let's see, Andrea has a question, but do you want to go slides? How do you want to organize this?
Yeah, I thought that we can compare about Shakura-Sunyaev and this new model. I've just got this paper with the new model yesterday, so I am not on the place to compare it, okay? Yeah, but I think we just already asked this this question, if we should forget about Shakura-Sunyaev, should we just start all work from the scratch using this new model, or how should we now approach from after this talks?
There are people in the audience that are doing modeling on small scale. I know some of you. So it'd be nice to hear your take on some of that.
Yeah, I think one.
You're one of them that I was.
I think this is like really impressive work, and the coupling of the spatial scales now starting to be able to make these comparisons of the observations is really amazing. And one aspect that maybe could also merit more discussion is something that we also discussed last week, which is the aspect of the self-regulation of the accretion. And Sylvain, you pointed out how the limited timescales, for example, winds don't really have the chance to properly propagate in these simulations. And obviously the same is true for the radiation and the jets. So I do wonder maybe what your take is, to what extent the accretion disk structure would be influenced if the large scale inflows would be regulated by what's coming from the feedback.
I mean, they tried to do that to some extent, but they are missing some ingredient. And the numbers are large, especially in that CAS paper. You know, it's non-spinning, it's 10%. And if it's spinning, 60%.
I guess I'm just wondering, because the jet is almost a little bit frozen in time, right? It doesn't have the chance to propagate to the larger scales and regulate them. That's what I mean. Long enough.
Yeah. I mean, it's 10% for the non-jets also, but it's true. I mean, it doesn't run long enough.
Was a halt maybe, but yeah, but they're very directional. Those seem to be in the plane. Structures are very large scales, and the jets are pretty much perpendicular to that. So I think if you were looking at self-regulation, you have to look at wing level scales. You could be kind of back to
Yeah, for sure.
controlling very large scale, coupling at larger distances.
So
I guess it was in weeks. We normally don't even think about weeks, right? Like, because our time steps are like vastly bigger than that.
Yeah, yeah.
So it's incredibly short term at the moment.
That's what I was. Yeah, so that this full coupling between the full range of scales that we're kind of thinking about also last week, I think it's still pretty difficult to achieve.
Exactly. So the coupling scales one way. There certainly isn't the other way.
Yes.
Exactly.
Andre, you had a question earlier. I didn't mean to.
Yeah, it's actually about point number 4 here. So I think in terms of testing these models, so I haven't read through all these papers, but I've looked through some of them. And the one thing that I was kind of trying to understand is what about sort of the most obscured quasars in AGN? What are the predictions for these models for these types of objects? So, and I'm talking about sources where, like, let's say, like 99% of the radiation is emitted in infrared. Right? I think a lot of the predictions now are for more like one AGN and quasars and so forth, but what are the predictions and how well do they replicate the features of the sort of the most obscure systems?
It's completely my question in the sense that basically a lot of the information beyond the simulation radius, not fully quantified yet. And I mean, they have this wonderful geometry in this particular objects, where they could make good predictions about the outflow, not the collimated outflow, but wide angle outflow. That's the outflows. And if you add the galaxy itself also, that make it. That information is there, but that stage.
Yes. Oh, sorry.
Oh, we had a question from the.
Yeah, okay, I don't know if it was a follow-up that you wanted.
I know it was, there was.
Okay, so let's go.
Yeah, maybe my question is about how to go about addressing the first question on how we go about selecting models. And this question kind of reminds me of the development of GR, like how GR came about and how it got adapted by making lots of predictions, and each one kind of satisfies the solar system test and things like that. So that brings me to sort of maybe the importance of models is to be able to predict something fundamentally new. I'm not sure to what extent that this new model is designed to reproduce everything we already know about or observed so far, and in what way it makes the different predictions that are not a consequence of the observation that got used to actually calibrate the model. So how do we go about, not sure if we, I'm trying to figure out what are the fundamental features of the model that are very different from Sakura-Sunyaev that will lead us to drop or consider dropping that one.
So, I mean, I guess I would say, yeah, I mean, what's needed here are actual testable predictions for real observational things, and that's certainly lacking, right? I mean, for me, it's trying to sort of do everything at once and explain, essentially everything that we want, in one model, as opposed to, having to add, something ad hoc and so on. But right, I mean, we need the ray tracing to produce the SEDs and the emission lines and the absorption lines, and basically something to simulate the variability and so on, right? So can this produce the kind of variability that we see in AGNs, right? And can it do it as a function of Eddington ratio? I mean, that's still work that needs to be done. I mean, I've had some discussions with them, and some collaborators have sort of said, hey, can you give us this end stage of the code, and then we'll run with it from there and do broad absorption lines and so on. And so that all definitely needs to be done. So I don't know that I would drop everything, but like I would be really interested in having people follow through, right?
Yeah, I would say that the Sakura-Sunyaev in general is a good starting point, just to to check what's going on. Okay, Benny was first.
And just to say, one of the points here on this slide is what can we use in other maybe larger models. It seems like the on picture is correct. If these simulations reproduce everything we know observationally, then I think we have simpler ways of incorporating the key physics.
Well, and so, I mean, the dome picture is not entirely correct, right?
No, I mean, sorry, as an improvement to the Sakura-Sunyaev, the slim disk, which is puffed up in the in the inner part, but remains kind of thin outward.
But where that's interesting in respect to your question, right, is like, so Doan's team, Mitchell has some nice work showing, okay, this model works reasonably well in this mass and accretion rate range, but when you go outside of that range, it doesn't work anymore, right? And so so a question would be, can we make this something that describes all of that? And in Chris Doan's model, she basically, the X-ray is always 2% of Eddington. right? And so if your system is 3% Eddington, then 2% of that is from the X-ray. And if your system is 100% Eddington, then still 2% is X-ray and 98% is in something else, right? So their model doesn't key in at 2% per se, but it is sort of on the order of a percent, and in a way that it's not inconsistent, at least, right? It doesn't necessarily fall out of the model, but
Yeah, you stress in your talk that the difference in the feeding, you, for example, mentioned X-ray binaries from overflow, AGN fed from elastic inflows. So there's the boundary conditions are important. You made that point. This paper is one halo, and it's one quasar redshift 2 or 3, I believe. So that makes me wonder if you have a galaxy that assembles differently from the specific object that was looked at in that paper, whether you could end up with a completely different solution. So since you've studied these papers so closely, is there a good reason to expect that this Parisian solution is in any way universal or expected to be some kind of attractor solution? Or could this be actually indeed highly sensitive to boundary conditions?
I don't think I can answer that. I mean, other than, yeah, I share your concern and interest in that topic, right? And it would be nice if they were simulating hundreds, thousands of galaxies, right? Not,
I guess I have a stronger view about that. I mean, they do start 10 to minus 15 gauss, disorganized, many feel. Then they decrease. So it's really, there's some measurements that suggest that it might actually be a bit higher than that in some region, at least. Just recent measurement last week, I think, and so anything larger will be even stronger toroidal. So I'm not sure you can avoid, as long as there's a seed community fields, you bring it in simple. I guess if it just accretes like this, maybe, but if it accretes conserving angular momentum, then it seems like it's gonna, I mean, you're the modeler. It would increase the strength of the many fields, and I would expect that.
Yeah, I mean,
become toroidal as they explain.
just to follow up on that, I mean, when I first started sort of talking to people about this, I mean, the reaction I got was, "Ugh, magnetic fields, forget it. I'm not paying attention to you." I'm like, no, really, there's no magnetic field, right? And then they're just following the physics, and this tiny magnetic field is basically, being magnet. So it's not like, oh, we need to have magnetic field to solve this, right? And so in that sense, it's pretty interesting.
Yeah, because my research has been about destroying stars in galactic nuclei and like tidal disruption events and stellar collisions. I have no choice but to think about the role of stars around AGN disks. So I think all these models do not consider all the interactions between stars and the disks. Because stars are penetrating the disks, and sometimes the stars are in the disk, make it more turbulent.
I mean, they discussed the problem of star formation, yes, but not.
At least the theoretical model using, I think, a Chakra-Shanae accretion model suggests that TDs can happen, every 10 or 100 years. So they could inject lots of energy into AGN disks. And I'm wondering if these new elements can change the picture, or
I think they would, because this this accretion disk from this Hopkins model is less massive, yeah. So then because in the Shakura-Shanae the disk mass is much bigger. So then I guess the effect is smaller. That's the intuition.
Fewer stars formed.
But some stars can actually settle down because of hydrodynamic drag. You have multiple.
Right. So I think you have fewer star form, and then you have less drag. But less massive disk. So I think that.
But you have also star clusters, I guess.
What's that?
Nuclear stellar cluster.
Pre-existing, or.
Yeah, I think.
That's probably doesn't change, right? But I guess for the TDE rate, the important factor is.
Dynamic drag.
Right, and so that would be
They said it.
less, I would think in this case, because the discs are less massive, significantly less massive, so the drag would be lower.
The volume is bigger. You spend more time in the disc.
So it's more like a surface density. And there's also some like a migration.
Interesting to see, actually.
Yeah.
When you had a what?
I wanted to also kind of discuss, PDEs in AGN and other extreme transients, exotic transients in this context. Let's say these nice things we've just seen are correct, and these are extremely short timescales you showed there, but not in weeks. It's great.
There are others that I didn't show that were on longer timescales.
Sure.
It included GR.
We do have some evidence in some systems for jet launching, delayed jet launching, or collapse of the X-ray corona and kind of recovery of the X-ray corona in at least some changing look AGN, which also has been interpreted, by the way, by H. Bigelman and collaborators as magnetic field reversal and recovery. So I think if we're fast enough with follow-up observations, we can tease out some predictions from these simulations about outflow launching, etc. We will be able to test it, but it's hard. After you see an accretion event, within 2 weeks, you see an outflow which wasn't there. Honestly, I don't know if it makes sense physically. But
Yeah, because the outflow scales are longer. They're a larger scale.
Right, so
unless it's the jet, unless you monitor the jet on the VLBI scale, I guess.
No.
I think that would be the test for that CATS model is you could monitor VLBI scale and if something comes out.
How long would it take to launch an outflow with the X-ray?
Well, it depends
An
where
X-ray kind of an outflow.
I mean, VLR outflow, then you have the VLR scale divided by the velocity, so it's long scale. Everything's going to get averaged out. So I think the UFOs actually is probably the next best thing after the jet. So you monitor UFOs with your favorite X-ray telescope, which aren't too many, Prism, I guess. And if it's variable, because that's really monitoring on short time scale and the scales of the months.
And I think in the context of the results you showed, you can think of it as a system temporarily crossing the Eddington limit and launching an outflow which wasn't there before. Or, I mean, maybe the geometry of the outflow will change on these short timescales. We're now monitoring, or
Yeah, I mean, I think they make some predictions about how things moves around. Well, before the GR, they have, even in the GR paper, they do show variation of the outflow geometry.
I mean, is it just like the angle is wider in there, or
They also
fluctuate?
they do all kinds of things also to the model. So the first term that I've never used, that I never used before, is axis symmetrized. I don't know if modelers do that, but for me, that's not a verb. But anyway, the axis symmetrized, so they align their model, the spin axis and the spin of the model. The symmetrized. They say it's only a factor of 10 degrees, of order 10 degrees. It's not a big factor, but they do it anyway. But that could change a little bit of the geometry, but it does move. Policy change.
I'm aware of the time and I see 3 more hands.
Just another sort of train of thought that I thought would be interesting to look into with this as well. So we've talked a lot about the large scale structure and the outflows, but one of the places we've used, especially to correct in the out model extensively in edge, measuring spin measurements of black holes, we're basically trying to measure this. So I think that's very interested to see how this model does for that, and whether we would have to do, if you went through the computer that, for example, let's say how good predictions for how the structure of the image changes with that.
I mean, that again, that CATS paper talk about it, but they don't make predictions.
They don't go there.
Yeah, I mean, that photosphere, the one with the jet, was all the way close to the center. So they say that if you're at the right angle, you'll be able to see RNK alpha and all that. In the other one, it's much further.
The problem is they have two spin values, right? But they're not exactly probing the whole program. It's
No.
to make some sort of clear.
Not at all, yeah, right, and so, yeah, but you mentioned it. Work to be done,
Sure.
just like.
Yeah, exactly. There was a.
Basically, it's like a conclusion that is about, to my thinking, that this model is very good and you have made up some predictions. But the thing is that we see a lot of different agents, a lot of different types. And so whether this model can reproduce all it, the thing is that of course it can be connected to the input parameter or the boundary conditions, like Tiago has said. The other thing is could be connected to, oh, they need to inject another model inside and to reproduce maybe this type or that type. So what kind of thing that is it will going on that is in the sense that they will just try to see different conditions and try to reproduce the agent, different types of genes, or if there's a need for additional models to try to reproduce different types.
I think they need to run a few more models, different initial conditions or different redshift. Yeah. Obviously, it's a lot of CPU just to do that one.
Yes, for sure.
And it was already 200 pages. I'm afraid to see the next series. Another tsunami of words.
So we need some CPU and some paper.
Just a quick one. I guess my hesitation doesn't come so much from magnetic fields as it comes from the spin, how these can reproduce. But we'll go for bias. I was also wondering how we can go into the sources that like circular accretion, so very, very slowly, how we can form and structure almost in the time scale, you know, the physical scales that we need for these massively radiating sources that we still in the that's another area. From my perspective, fewer than 10% AGN to produce X-ray and not university. So I come from the other end of the spectrum. In the nearby universe, maybe we will appreciate rates. I think it's important to.
So, I mean, I had a very like an hour and a half conversation with Phil. You know, a lot of it was on radio and jets, and so for me, those are particularly interesting because actually fewer than 10% of Sloan quasars have jets. Fewer than 1% have jets, right? And so I was trying to understand, okay, how do I understand this? You know, I mean, it's a longer term conversation, but that was sort of where something was missing, and they did end up adding a paragraph at my request about the radio, but basically just sort of saying, yes, you know, we acknowledge that this is something that we need to think more about. Right?
I think that that landscape has changed. What we see with the deep low fire, that all the quasars have emission, but they have jets, not necessarily clear, but they have something again. The canonical numbers we see now in the low for depths, that's 30% of all radio emission. So that's
so
that couldn't be yes or no anymore. And if you go deep enough.
I mean, my bias would be there's multiple sources of radio, and I used to think it was all jets, and now I think it's mostly not.
So I'll just chime in to advertise that Alma also find jets now, and we hear from Victoria in the afternoon about this. And I'm aware of a time. Vinny, did you have one last comment you wanted to make?
It really is a comment. Sorry. It's almost exactly 20 years since the last time Phil Hopkins solved the universe with an avalanche of long papers which seem to explain everything. It's amazing he's still able to do this in an innovative way. I think it would be great if, well, not me, but other talented people in the room can challenge some of this or reproduce it with other codes, with other approaches. Then us, the observers, fine, we know what to do, right? But the very least to see this happening on other machines in other campuses, and the science should be done.
We'll try, but it'll be a challenge.
Fine. Please do.
All right, so if that's okay with my members, I suggest we'll break now for half an hour call. So let's come back here at 45.